Okay, so we're going to continue on here. Last time we finished up chapter 13. So we're off to chapter 14. So this now should be exam 2 material. Exam 1 material was chapter 13. And exam 1 is next Thursday, I believe, a week from today, if I'm not mistaken. So um, make sure you're working on the homework and all that good stuff as well. The box for that should be up there very shortly for you to turn it in and upload it. All right, so chapter 14 is a really long chapter. I would say in your book, they kind of combo everything in chapter 14. So in a lot of textbooks, they will break chapter 14 into like two different chapters. So there's sort of a first part and second part that we'll do here. So eventually we'll get through chapter 14, but we'll be here for a while, kind of going through everything that's in this chapter because it's essentially kind of two chapters of one in your book that we use. All right, so chapter 14 is going to talk about acid and bases, and let's talk a little bit about acids and bases and some of their properties. Acids have a sour taste. Vinegar, for example, a major component is acetic acid, which is a weak acid. Citric acid there in fruits. As you may remember, acids do react with certain metals to produce hydrogen gas in a singles type replacement reaction. So if you have something like hydrochloric acid, it will come in and kick out the hydrogen, and that's going to make zinc chloride and some hydrogen gas being generated. In this particular case, I'll balance it like I'm a chemistry teacher. We'll do that there. And this is again a single replacement. As you may remember, uh, if this reaction did take place, that means whatever is coming in is more reactive than what it's replacing. And this guy has no charge. That's a positive, negative. And zinc, when it does make a charge, because it's a metal, obviously will make a positive charge. So that's why it replaces the positive hydrogen in this case. And in addition, acids can react with carbonates and bicarbonates to produce carbon dioxide gas. Again, you could have something like a little hydrochloric acid, a little sodium bicarb or sodium carbonate actually here. And again, this is going to do a double displacement reaction where we will make H2CO3, which is carbonic acid, and we'll make a little sodium chloride here, maybe balance it up as well, put a 2 there. And it is that carbonic acid which rapidly goes through a decomposition reaction to form H2O and CO2 gas, kind of plop, plop, fizz, fizz that you typically will see. Um, Bases, on the other hand, they feel very slippery. A lot of soaps are contain bases. A lot of like drain cleaner and that type of stuff is basic along the way. Before we go too far, just a reminder, which again you should hopefully know, but in terms of acids and nomenclature, right, to name them, as you may know, acids naming is all about oxygen and whether or not there's oxygen in the formula. And if the answer is there is no oxygen in the formula, the acid is hydro something ic acid. So something like HCl. And by the way, acids are usually have the aqueous symbol next to them to indicate that they are in a aqueous environment or water environment, and it's sort of ionic in that sense. This obviously would be hydrochloric acid, right? HBr would be hydrobromic acid. Right? Now, if it does contain oxygen, it usually will contain a polyatomic ion. And as you may remember, polyatomic ions usually end in ate or ite. And if it does contain oxygen and your polyatomic ion ends in ate, your acid would be something ic acid, like HNO3. NO3 is nitrate, and this would be nitric acid. H2SO4 SO4 is SO4 2 minus, which is sulfate. That'll be sulfuric, bless you, acid in this case. By the way, the cation for every acid is H plus. So H plus is always the positive guy, right, in any acid. And that's why in the case of sulfuric acid, right, we have two of them because sulfate is -2. So to balance the charge out to 0, it has 2 hydrogens in that case. If your polyatomic ion ends in ite, your acid would be something OUS acid. So like HNO2. NO2 is nitrite. That would be nitrous acid. Same thing if you did H2SO3. That is sulfite, SO3 2 minus, so it'll be sulfurous acid. Question on how to name acids. Hopefully that's review, I hope, yeah. So that way, you know, when you have an acid, you just go, that thing over there, whatever that thing is, right? So you know how to name it. All right, so let's get back into sort of the main part of this here, which is the early sort of definition of an acid is really a substance that can produce H plus ions in solution. And that's the key. The key is free H plus ions in solution. So not attached to anything, has the ability basically when it goes for a swim, basically to produce H plus ions in solution. That's what's going to make it an acid. Um, and one of the things that's important in sort of acid-base chemistry is H plus ion, which is the hydrogen ion, and H3O plus, which is the hydronium ion, polyatomic ion, are basically the same thing. So they are used interchangeably in formulas. They're also used interchangeably in equations and stuff like that. So really anywhere you have an H3O plus, you could kind of put an H plus. Anywhere you have kind of a H plus, you could put an H3O plus and vice versa. Now, why would you perhaps get an H plus versus an H3O plus? It really is sort of your preference when you write the reaction or the equation that's going on. So really, if we take a look at what we have here, which is hydrochloric acid in this case is really just dissolving in water to basically make the acid. And you could show this as basically the acid here sending that H plus over to water. And if you include the water in the equation, you will produce H3O plus in your sort of product side there. And that's basically the acid part. So, I mean, that's the same thing as if basically my beaker above as saying I have H3O plus floating around in the beaker. It's the same thing as having free H plus. You could also, because HCl, for example, is a strong acid, or even if it's not a strong acid, sometimes people will write, and what we're looking at in this equation is what is sometimes referred to as the dissociation of the acid, which is basically the acid breaking apart in a water solution, basically in our water environment. You could write the kind of dissociation of this acid by leaving the water out of the equation, and you would just break it apart into its ions, which in this case would be H plus and Cl minus. Both of these equations are basically equivalent to each other. And instead of H3O plus in this case, because we didn't include water in our equation, we get H plus. So again, these two guys are basically the same thing. It's talking about the acid part of the solution, basically, in this case. I personally, most of the time for acids, do not include the water, but if you want to, again, the only difference is you'll just get H3O plus on the other side, and it's all good. It's the same as H plus. Now, that is essentially what makes something an acid. We also will see that sometimes H plus is referred to as a proton as well, and it's referred to a proton as well because hydrogen has only a proton and an electron, right? It has no neutrons. So the only way it can become positively charged is to lose its electron, and that leaves it just a proton. So also very commonly in acid-base chemistry, H plus is referred to as a proton. Because of that, it pretty much only has a proton left. So the Arrhenius definition of an acid, again, is something that really has the ability to produce that free H plus in solution. And a Arrhenius base is something that can produce OH minus in solution. So for something to be a base, it has to have the ability to produce free OH minus basically in solution. And here with ammonia, we actually see that ammonia is actually a weak base, very common weak base. And in this particular case, what's going to happen is the water will actually send some hydrogen over to it, and that's going to produce basically our hydroxide here. Now, ammonia here is a weak base because, frankly, it does not have OH minus in its formula, right? So it cannot just like go for a swim and fall apart and get the OH minus released. It has to go do a little reaction with water basically to produce that OH minus. And that's going to make it a lot weaker of an acid, hence the arrows heading in both directions. It sets up an equilibrium in this case. This is a reversible sort of reaction. Now, a lot of strong bases, something like sodium hydroxide, sodium hydroxide really is a strong base because, frankly, it's carrying the hydroxide with it, right? It doesn't need to go find it. It doesn't need to go react with it. It pretty much just needs to go basically for a swim, and it's going to break apart into hydroxide, and it will fully break apart because it is a strong base into hydroxide and sodium in this case. Because it's a one-way street in this case, it's going to produce a lot of free OH minus in that solution really quickly. And that is why it's considered a strong base versus our ammonia here, which again has to go find water, set up this equilibrium, and going to produce a lot less free OH minus in solution. And it's going to be a much weaker base. I would say on our periodic table there, we can find our strong bases in group 1 and group 2. So when we look at group 1 or group 2 on the periodic table, those are the alkali metals, our alkaline earth metals. Again, the word alkaline means basic, basically. So that's where a lot of strong bases come from when they're hooked up with hydroxide. If you just go up there where lithium is, like sodium, like potassium, hang a right there to calcium, strontium, barium. Any of these guys kind of group 1 and group 2 that have hydroxide on them are most likely going to be a strong base in this particular case. Now, this was a good sort of definition for acids and bases, the Arrhenius definition, but it was really limited. And he did a lot of work with bases that basically contain hydroxide in them. And as we saw there with ammonia, uh, bases don't necessarily have to have hydroxide in their actual formula or in their sort of on them, if you will. So a more general definition of an acid base is the one that most people sort of deal with is the Bronsted Lowry definition of an acid and a base. And in a Bronsted Lowry definition of an acid and a base, a acid is a proton donor. So that is something that will give away an H plus. And a Bronsted Lowry base is something that will accept an H plus, so something that will accept the H plus. So in this case, if we look at ammonia, and I would say unlike when you need to write reactions for acids breaking apart, you a lot of times don't need to put the water into the equation. I will say for the base, it's a good idea to kind of put the water into the equation and kind of visually see where the hydroxide sort of comes from. So this ammonia here is going to act as our base. Water is actually going to act as our acid. And again, it is the water going to send the H plus over to our base. The result of that is the NH3 will gain that H plus and become NH4 plus on this side. And it's really important to make sure that you think about H plus with the charge as well. So people oftentimes will remove the H or add the H and forget about the charge. the charge is really important, right? So if you lose a positive charge, you become one more negative, right? Because now you have one less proton and more electrons. And if you gain a positive charge, again, become one more sort of positive in that direction. So the charge does change. So we can see here NH3 was neutral. It gained the H and the plus and ended up as NH4 plus. The water here was neutral. It lost an H plus, which means it becomes one more negative there and becomes hydroxide. The Bronsted Lowry definition creates actually pairs of substances on both sides of the equation here. So the base on this side is related to what is known as the conjugate acid on the other side. And the acid on the left is related to what is known as the conjugate base on the other side. So always, for the most part, I would say, your regular old acid and bases are found on the left-hand side of the arrow. Your conjugate partners there, the conjugate acid, conjugate base, is found on the right-hand side of the arrow. Now, in order for these things to be related to each other, the absolute only difference that you could have is this guy right here. So you could only have a difference of 1H plus. So that can be the only difference between two things for them to be related to each other in this Bronsted Lowry conjugate acid base pair. If it's more than 1H plus, if there's some other difference besides the H plus, they are not related to each other. Questions on that there? So we also saw, for example, earlier we included the water there in our dissociation of our strong acid here. And again, in this case, this is going to be my acid. This is going to be my base. And the HCl is going to send, again, the H plus over to the water. That's going to make here Cl minus and our H3O plus. Once again, this side is my acid. This guy here would be my conjugate base. My base is my water, and my H3O plus would be my conjugate acid. Again, in this case, the absolute only difference between each of those partners is 1H plus. As we go from the acid to the conjugate base, it has one less H plus. That's because it gave it away. And as you go from the base to the conjugate acid, it has one more H plus because it accepted it. And that is where we end up. We also see something here that we'll talk about as we go through this chapter, but in this particular reaction here, or not really reaction or dissociation, what we see for water is it is acting as a base. But if we look at the one we just looked at on the previous slide, water in this case is acting as an acid, right? So in this case, on the previous slide, water was an acid. And in this one, water is a base. And there are substances, and water is one of those, that can act as an acid or a base. And those things are known as being amphoteric. So an amphoteric substance is a substance that can act as an acid or a base. Typically, something like water are typically things that have a hydrogen and a negative charge. A lot of times can act as either an acid or base. And things that, again, like I said, have kind of like a hydrogen and a negative overall charge with some other stuff there, can act as an acid or a base, like HCO3. It has the H to give. It also, because of the negative, can accept the H plus pretty easily as well. So it can kind of go both ways. We will talk about a little later on how you could determine kind of which way it will do that. Will it act as an acid? Will it act as a base? So there are certain things you can look at to help you determine, am I going to see it in sort of doing the acid part, or will it do more of the base part in this situation? questions on that there? All right, so why don't we try one here? So for each of the following, are these conjugate acid-base pairs? So take a look at each of them, decide, are there any pairs here? Okay, let's take a look. So really to determine if these things are basically Bronsted Lowry acid conjugate base pairs, this right here is the only difference that there should be. So if there's anything more than an H plus difference between those two, they are not related to each other in that sense. So obviously here, if we take a look at the first one, we got HCl and OCl minus. The difference here is one H plus, but there's also a difference of an oxygen, right? And obviously the other one doesn't have an oxygen. So that is a negative there on that. They are not going to be pairs because of it. If we look at H2SO4 and SO4 2 minus, are they pairs? They're also not pairs because the difference here is not one H plus, but it is two H pluses, yeah? So for example, hydrogens do come off, by the way, one at a time, as we'll talk about. They don't just both drop off at once. H2SO4 is a diprotic acid, which means it basically has two hydrogens to give. And the process at which that happens is something like this. H2SO4 will first drop off one hydrogen and make HSO4 minus. Then that HSO4 minus will then drop off a second hydrogen and make sulfate in this case. And that is a stepwise dissociation that occurs here with something that is a polyprotic acid. That is why if we look at this guy and this guy, these two guys would be partners, right? Because the only difference there is that one H plus. If we look at this guy here and this one here, they also would be partners as the difference is only H plus. But like in our question that we have here, we are kind of jumping too far this way. We are a double H plus difference there. And again, that would not make them partners in this case. So no deal on that one. We got NH4 plus and NH3. The only difference here is one H plus, right? So you could either take the H plus off the guy on the left and you end up with NH3, or you could put the H plus on the one on the right and you end up with NH4, right? So that's the only difference between them. So we're gonna go, yeah, on that one, it looks like. And H3O plus OH minus, difference here is again two H pluses, right, in this particular case. So would not be a pair there. The one that really binds those together is the middle guy is water, yeah. Water's got the middle guy there between those two. That would be partners to both of those guys, but in this case, there was no water there. Obviously, 3 was good, so 5 no good, yeah. Any questions on any of those there? Take a look at this one. Aniline was isolated in the 1800s. What would be the formula of the conjugate acid in this case? All right, so when we're doing this one, what we want to think about is maybe it'd be helpful the relationship we talked about in terms of Bronsted Lowry. So on the left-hand side, we have our acid and our bases. On our right-hand side, we have our conjugate base and our conjugate acid, right? Or however you want to write it. So the acid on this side is related to the base on that side. The base on that side is related to the acid. So in this particular case, we're asked to write the formula of the conjugate acid. And again, if they weren't nice enough to tell you it was a base, which sometimes they are not nice enough to do that. What we want to think about is we want to end up here at the conjugate acid, which if we go backwards means what we are looking at is a base. And what we're looking at is a base, and all we have to do is the Bronsted Lowry definition of a base, which is something that will accept an H plus. So we basically got to put the H plus on. So our goal here is to either put it on or take it off the H plus, and that's what we would need to do here. So we just got to basically put an H and not just an H, but also the plus as well. So again, when you gain the H plus, you become one more positive. It started as neutral. and ends up at one more positive in this case. Is that 2 maybe? Yeah, 2 looks like in that case. Yeah. Any questions on that? So sometimes that's helpful when you're asked to write the conjugate acid or conjugate base. If you're not sure what you're dealing with, just think about it backwards of, is that an acid or a base, and just follow the Bronsted Lowry definition. So for example, if we had HCO3 minus, and I wanted the conjugate acid, and I want the conjugate base, why don't you take a second and write the formula for each of those. In both cases, we're starting with the same. Okay, so let's take a look. So obviously we're going to start with each of these here. So we'll do our conjugate base first. So once again, we want to do the conjugate base, which means in this particular case, it's going to act as an acid. And again, the definition of an acid is going to get rid of the H plus, right? So that should end up with CO3. Again, when we lose the H plus, we become one more negative. So we were starting at -1. So we do end up at -2. And again, the charge thing is somebody that sometimes people mess up a lot on. In the case of our conjugate acid, much like in this problem, we would think about our conjugate acid going backwards. Once again, much like in the problem, this is going to act as a base in this case, and it's going to add an H plus in there. And that will put our H2CO3, again, +1 and -1 here is going to equal 0. So we basically end up with no charge when it's all said and done. Any questions on that there? Okay. All right, so let's talk a little about acid-base properties of water. And water, as we talked about earlier, can act as an acid or a base. And because of that, water can react with itself. And in some cases, one water will be the acid and the other water will be the base. It's kind of what's happening with water all the time. And in this case, what it's going to form is H3O plus and OH minus, or you could just simply break it down here into H plus and OH minus. Once again, uh, you can also do your H3O plus and OH minus in this case. And as you saw there, a couple of waters will do that for you. Yeah. It is a reversible reaction, which means it can set up an equilibrium, and that equilibrium is an equilibrium constant we could write like a normal equilibrium constant, which is our products over our reactants, which in this case would be the H plus concentration times the OH minus concentration. This has to do with water, so not surprisingly, it is called Kw there for water, and that's the ionization constant for water. Just like we talked about before, you could also do this with the H3O plus and the OH minus part. It is again the same deal. This is really your acid part of your solution, your base part of your solution, acid part, base part, and again, that H plus and H3O plus, same deal here, basically. Now, we do not include, obviously, our reactants, just like a normal equilibrium constant, right? Because it is a pure liquid. So again, just like we did previously, we would not include it. Remember that pretty much all K values or K expressions are the same. They're all just products over reactants. They kind of follow the same rules. Um, And again, in this situation, one of the waters is going to act as the acid and one's going to act as the base, producing our conjugate acid base pairs in solution. And as we will talk about, really the concentration of the H plus versus the OH minus in the solution will allow you to determine whether or not the solution is acidic, basic, or neutral along the way. Obviously, if you have more of one versus the other, is going to be either acid or basic in that particular case. And that is again known as Kw. And for the most part, it is an equilibrium value. And that means it is specific for temperature, like we talked about with K values, right? So technically speaking, this is a K value, and it does equal, for the most part, 1 times 10 to the minus 14. So that is sort of a constant value that you sort of have. But as I was saying a second ago, it is technically an equilibrium constant. So if you do find yourself not really at 25 degrees Celsius, the value of kW will be different because it again does change with temperature. But I would say probably 99% of the time you could roll with the 1 times 10 to the minus 14. If you happen not to be at 25 degrees, usually the problem will give you like a kW value to use or refer you to a table maybe to look it up at that particular temperature. So usually they'll give you some type of information like, hey, we're not really at 25 degrees. Maybe go look it up, or this is the value to use for kW at this temperature. Other than that, if they really don't mention too much about temperature or say anything like that, you're fairly safe in pretty much all cases to roll with the 1 times 10 to the minus 14. What does that allow you to do? Well, frankly, if you rearrange this, you could take the concentration of H plus is equal to 1 times 10 to the minus 14 divided by the concentration of the hydroxide. So if you know the OH minus concentration in that solution, you could calculate the H plus concentration by doing that. The good news is it's pretty much the same calculation regardless of which one you're given. So if you know the H plus concentration, you could calculate the OH minus concentration by basically divided by the H plus concentration in that case. So that is the calculation you can do. Once again, you definitely want to make sure you're using your exponent button on this. Otherwise, you're going to be in some trouble if you are not. So what can this help us determine? Well, if the H plus concentration equals the OH minus concentration in that solution, by the way, at that point, they would both equal 1 times 10 to the minus 7 molar at that point. It will be a neutral solution. If the H plus concentration is larger than the OH minus concentration, that's basically your acid part is bigger than your base part, your solution will be acidic. And if the hydroxide concentration is larger than the H plus concentration, so basically your basic is larger than your acidic, then it will be basic. The relationship between H plus and OH minus is an opposite relationship, which means as one goes up, the other goes down. So as you have more H plus in the solution, you have less OH minus in the solution, and vice versa. If you increase the amount of OH minus you have in the solution, the amount of H plus will go down. So again, it works obviously in both directions there. So if the H plus goes down, the OH minus goes up. So they always work sort of in opposite directions. Questions on that there? Yeah. The truthful answer is most of everything that we measure in temperature, a lot of times it's more of a metric system. Like you think about thermometers we've used probably in labs and stuff like that. It's usually in degrees Celsius. So that's usually very commonly sort of what we use for a unit of temperature. Although the relationship in a lot of sort of chemistry sort of formulas is Kelvin. And that relationship is sort of an absolute temperature scale, and it's used in a lot of calculations because it's that it kind of goes zero out at absolute zero. So it's kind of that, as opposed to our Celsius temperature that can kind of go really up or negative and that type of stuff. So that's why it's sort of used like that. And it is what is considered sort of a standard condition, 25 degrees. The actual 25 number uh, is a lot of times when you look up at tables and stuff like that, they oftentimes are done at that temperature, and it's sort of like a room temperature type of thing. Is that why we kind of use a lot of times like 25 degrees Celsius? Other questions? All right, so why don't we try one here? What is concentration of hydroxide in this solution if it is 1.3 molar hydrogen ion? All right, so let's take a look. So obviously here we're going to use our Kw, which is the H plus concentration, and the OH minus concentration. And again, pretty much a constant value of 1 times 10 to the minus 14. Good news, like I said before, is pretty much the same calculation regardless of which one you're given. So basically just going to divide that guy to the other side there since we are given the H plus concentration of 1.3. And we'll pop that in there. Again, we want to make sure exponent button being used. 1.3. That's going to give us a 7.7 times 10 to the minus 15. It does need some units as it is a concentration in this case. And again, we could compare in this case our H plus concentration to our OH minus concentration. And clearly in this case, our H plus concentration is a lot larger than our OH minus concentration. And it definitely would be an acidic solution, which does make sense since that's an acid. So that would all make sort of sense together. Any questions on that there? All right, we will wrap that up for